Hey guys, I'm John and welcome to Respect Your Intellect. The deepest that mankind ever dug into the earth is just over 12 kilometers deep, so did you ever wonder how we know so much about the core of our planet? This is a very popular argument among flat earthers as well, so we're going to be addressing that in this video by talking about the science behind it all. Let's get started. Before we get started, you guys can now find my website at respectyourintellect.com, so be sure to check that out. To start off, let's talk about some of the more observational evidence and common sense. When we look out in space, we can predict just about every movement due to our knowledge of gravity. We can also determine the mass of an object by the gravitational effects it exerts on other bodies. In the case of Earth, we know that its mass is 5.972 septillion kilograms, and we use this successfully for tons of calculations. We can use it to determine the gravitational pull at the surface, the escape velocity we need to reach space, predict all movements to accurately predict eclipses down to the second, and so much more. Since we also know that there's nothing of that mass at the surface, it's very easy to deduce that this mass is below us towards the center of the Earth. For the composition of the core, we know it can really only be made of mostly iron because it's the sixth most common element in our galaxy. This abundance of elements in our galaxy can be directly observed using spectroscopy just about anywhere we look, and they're also easily explained by a star's evolution. With iron being so common and universal, we should see a lot more of it at the surface than we actually do. So this can really only be explained by most of the iron having sunk towards the core, and it's a great correlation because it's also the heaviest of the common elements in our galaxy. As for the rest of the Earth, it's made up of rocks called silicates, and in 2013 we were able to successfully show that liquid iron can be squeezed through silicates. We did this by squeezing the silicates with diamonds, and we observed that the liquid iron actually was able to make its way through. This also correlates well with the other observations because iron is the heaviest element and it will sink if it can pass through another lighter material. If you're not convinced just yet, hold on to your hat because now we're going to get into much stronger evidence which comes from seismology. Seismology is the scientific study of earthquakes and the propagation of elastic waves through planetary bodies. The way that seismology works is that when an earthquake happens on one side of the planet, we can detect waves on the other side as they move through the Earth. You can imagine this like hitting the planet with a giant hammer on one side and listening on the opposite side for the vibrations. In 1960, there was an earthquake in Chile called the Valdivia earthquake, and it was the most powerful earthquake ever recorded at a magnitude of 9.4 to 9.6. This earthquake was strong enough to be recorded by just about every seismic station on Earth. The routes taken by the vibrations on their way to each station gave us a ton of information because they all took different routes through the Earth and sounded different at each station. This gave us a ton of information on the makeup of our planet because we had data for a ton of different paths. In the early history of seismology, we also realized that some vibrations called S-waves were going missing. This is because S-waves are only able to reverberate through rock and not through liquid. This was happening for all S-waves that took a path through 3,000 kilometers deep, so it means that as of that depth it can only be liquid. In the 1930s, we determined that another type of wave called P-waves were able to travel through the core and be detected at the other end. This is when we discovered and theorized the inner core, which starts at about 5,000 kilometers deep, and that it was solid due to the tremendous pressure from gravity this close to the center of mass. This was confirmed in 1970 with much more sensitive seismographs. We were able to detect that the P-waves were traveling through the core, were deflected off the core at angles, but were still heard on the other side of the planet. Other than earthquakes, we also increased the accuracy of seismology with nuclear weapons that could also be heard on the other side of the planet. As countries learn more about the nuclear capabilities of rival countries, we also gained a lot of knowledge about the core of the Earth through this process. You should take a second right here to click that like button for seismology. Next, in 2013, we determined that the melting point of pure iron at pressures around the core is 6,230 Celsius. However, there are other materials in the core which brings down the melting point a bit lower to around 6,000 Celsius. For comparison, this is just about as hot as the surface of the sun. This heat comes from all the impacts during the formation of the planet, as well as friction from the movements inside the planet since we first formed. We don't lose this heat very fast, just about 100 Celsius per billion years or so, because there isn't really anything to pull the heat out of the planet. So the way we lose heat is by processes like radiative cooling, which is very slow. The heat in the core also affects how fast seismic waves can travel through it, so that's also important information to have. As of right now, we know that the waves are traveling slower than if it was pure iron in the core, so we suspect that there's also a lot of nickel there. Even when that's figured in, it's still not a totally perfect fit, so we also expect other elements to be present like sulfur and silicon. Right now, we only have an answer that gets really close, but we're still continuing the efforts to be able to find the perfect fit. The answer is likely just about getting the precise temperature, pressure, and combination of material so that everything is explained while still making perfect sense. Once we have that information, we'll make some predictions based on that and test it out through experiments to see if it holds up to all scrutiny. Next, we also have tiny daily fluctuations when it comes to the length of our days. We have about 1 millisecond of fluctuation that's caused by the dynamic or constantly changing atmosphere. There are many complex things that help cause this fluctuation, but one example is water evaporation and precipitation. Since the mass of that water still exists, the Earth will slow a bit if that water mass is further from the center. This is a bit like a figure skater that turns faster when they bring their arms in for a smaller radius and slower with the arms out for a larger radius. In this example, we start with a curved path that translates to the initial spin that we see here. This is somewhat slow because the radius is still large with the leg fully extended out. Then, as the radius decreases when she goes into a sit spin, it translates to more velocity for the rotation. Next, she minimizes her radius even more and her rotation really accelerates. And finally, just as she exits, she pulls her arms out again to slow her rotation to a more manageable speed. The Earth does the same thing through many different processes, and the fluctuations that they cause is measured every day. This gives us a graph just like this that can help us keep track of everything. On top of daily fluctuations, we also have longer fluctuations of about 4 milliseconds over 65 to 80 years. Those fluctuations are explained by the interactions of the core with the mantle of the Earth. They also correspond with some magnetic field fluctuations that we can observe directly as well. Next, we have plate tectonics that gives us a lot of information about the composition of our planet as well. This idea of having large plates moving that we call continental drift was developed in the beginning of the 1900s. This idea was later confirmed in 1960 by the observation of seafloor spreading. Seafloor spreading is the process of lava coming up from between two tectonic plates, forming a ridge as it cools and pushing that ridge outwards from the center as new lava flows up. This also agrees with everything else about the Earth's core that we already went over. Next, we also have a lot of magnetic field observations as well. Edmund Halley, who also discovered Halley's Comet, was the first to show in 1962 that the Earth's magnetic field has a westward drift. We can also use past lava flows to directly observe past magnetic field directions. The way this works is that when lava flows erupt and cool, they acquire a memory of the Earth's magnetic field at that time. These serve as recordings of magnetic field directions of past periods on Earth. This is also one of the reasons why we know that we're likely in the process of a magnetic pole reversal at the moment, and that it will likely flip within the next 1,000 years. With all this information linked together, we can also determine a few other things. The Earth's inner core is close to the same size as the Moon. The inner core is currently spinning eastward faster than the Earth spins on itself, so we say the inner core is super rotating. We also know that the outer core is currently spinning westward at a slower pace. With all this information about the core, we were able to create an experiment to generate a magnetic field in the same way as the Earth does on its own. It's called the Molten metal magnet experiment. This experiment shows how the movements create a feedback loop that dramatically amplifies the small random magnetic fields that always exist in magnetic materials. This happens because the heating and cooling causes the molten iron to rise and sink in the outer core. This motion, as well as a bit of contribution from the Earth's rotation, creates electric currents. These electric currents are what amplifies the magnetic field enough that it can surround the entire planet and reach space. The molten metal magnet experiment is an improvement on earlier experiments because it uses truly turbulent flows in the same way that the planet does. In other words, the flows themselves don't need to be strictly controlled in a lab to make the magnetic field happen. It's generated even with a very natural turbulence. There's a common misconception with conspiracy theorists like flat earthers where they think that direct observation is always the only way to know something. There are a lot of things that we can't see, but we can deduce their existence and make predictions based on what should happen if it was truly the case. Once predictions get verified and confirmed, it's even better than just a simple observation that can be biased. I have an earlier video on the methods of reasoning in science that you should check out for more information on this. Predictions are a very central part of science, but simply observing something is only a small part of the entire process. Science is about being able to predict the future by knowing how things behave in reality. If you drop something, it'll go down and touch the ground at that exact time. If you throw something, it'll take this exact parabolic path and take this exact amount of time. If you submerge this ball, the water will be displaced by the amount of volume of the ball. If you look at that position in the sky from this position on Earth at that exact time, you'll see an eclipse that looks exactly like this. When it comes to the Earth's core, we have a lot of evidence and predictions that were made and confirmed, so our degree of certainty is very high on this information. Direct observations can help in clarifying things and can help lead us towards making predictions, but they don't constitute science on their own. You can even make predictions about past events that, when confirmed, still hold up to scrutiny as new data comes in and leads us to predicting future events. But all in all, if you can't make predictions, then it simply isn't science. So how much of this did you already know, and how much of this did you find helpful? Let me know in the comments. If you like this video and want more, be sure to like this video, subscribe, and click that notification bell. For everything else, you can now just go to respectyourintellect.com and everything will be available there. You can let me know in the comments what you think of the new site as well. Until next time, thanks for watching, and remember, respect your intellect.